Hello, in this video we will discuss a portion of the paper on elements of modern physics. The topic that we will discuss is a collection of identical entities using a classical approach. So here we have the syllabus that we will cover, and right here are the two reference materials that I have used. The first idea that we will discuss is thermal equilibrium. Two bodies in thermal contact exchange energy in the form of heat. This exchange continues until thermal equilibrium is reached. The zeroth law of thermodynamics tells us that if two bodies are each in thermal equilibrium with a third body, then they are themselves in thermal equilibrium with each other. Suppose this is in thermal equilibrium with this, and this is also in thermal equilibrium with this, then this implies that these two bodies are themselves in thermal equilibrium with each other. This allows us to define a common property of all these three bodies, the temperature. So if these three bodies are all in thermal equilibrium with each other, then they all must have the same temperature. In addition, it allows us to design a thermometer and measure temperatures of various bodies. Before thermal equilibrium is reached, heat flows from the hot body to the cold body, and this is an irreversible process, and this process through which two bodies come into thermal equilibrium is called thermalization or equilibration. When thermalization is going on, the macroscopic properties of any body keeps changing, and once thermal equilibrium is achieved, macroscopic quantities achieve steady values. Next, we talk about a large collection of identical entities. So we will start the discussion by thinking about 10 identical coins. Now, if we look at a system of 10 such coins lying flat on a table, then this system has 2 to the power 10 possible states. So each coin has two possible states, head or tail. Since we have 10 independent coins, there are 2 to the power 10 possible states, and these states are called microstates of the system. So a particular microstate can be a particular sequence of heads and tails. For example, head, tail, head, 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 tail, tail, tail. Another one can be head, tail, 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 head, tail, 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 head, head. And a third one can be head, head, and all 10 heads. It may be surprising that all these microstates are equally probable, and the probability of having any one of these microstates is 1 by 2 to the power 10. This one looks very unlikely to occur, but a particular sequence of heads and tails, for example, this one is as unlikely as all heads or as likely as all heads, and the probability is just 1 by 2 to the power 10, which is approximately equal to 0.001. If we put together many such microstates, we get what we call a macrostate. So a given macrostate corresponds to a collection of microstates, and examples of macrostates can be, for example, 5 heads or an even number of heads, etc. So a macrostate which has more compatible microstates is more probable than one which has less compatible microstates. So for example, a macrostate consisting of 10 heads has just one compatible microstate, which is the one listed over here, and that one is very unlikely because there is just one microstate corresponding to it. However, this one with 5 heads is very likely because there are many ways of getting 5 heads. For example, the first 5 can be heads and the remaining can be tails, or every alternate one can be head, and so on. Another class of a large collection of identical entities are what we call thermal systems. An example of a thermal system is the system of identical gas molecules filling up a room. So here the microstate can be a specification such as the information about the positions and velocities of every gas molecule in the room. For example, the first one can be at R1 with the velocity V1 and so on, and the nth one can be at a position Rn and moving with the velocity Vn. So this collective information specifies one microstate of the system, and using it we can calculate various quantities associated with this microstate. A macrostate, on the other hand, is a specification of some macroscopic quantity, such as the volume of the system or the temperature of the system or a combination of some macroscopic properties, and based on those there may be many possible microstates compatible with one such macrostate. In a macrostate, the measured value of some macroscopic quantity is the average of the value of that particular quantity in all the compatible microstates. So for example, we can write this as an equation. So the measured value of, say, some property or some observable O would be 1 by number of compatible microstates times the sum of the value of this in the ith microstate. So this is the measured value of this quantity O in a particular macrostate for which there are this many microstates. To summarize, in this video, we started with a discussion of what thermal equilibrium is and what we mean by equilibration and thermalization, and the fact that macroscopic quantities in a system keep changing until thermal equilibrium is achieved, after which they acquire steady values. Next, we talked about a large collection of identical entities, and we introduced the idea by talking about a collection of coins, and we introduced what are microstates and macrostates. Next, we talked about thermal systems and what microstates are for thermal systems and what we mean by macrostates. In the next video, we will talk about what temperature is and how we define it and some other ideas.